So last time we talked about strain measures, namely the Lagrangian or Eulerian strains. And we showed how they both recovered the small strain in the limit of small displacements or displacement gradients. Okay, so we're not going to do a whole lot with strain rate in this class, but particularly when we do plasticity modeling, we typically do it in rate form. In other words, just to remind you what we're doing here, right? We develop some strain measures, and those strain measures combined with a constitutive model can give us stress, okay? And then that stress we plug into the field equation, conservation of momentum, and that's what we solve, right? We'll get to the field equations later, but that's sort of the big picture of what we're doing, okay? So typically when we do plasticity modeling, we have constitutive models that are in rate form. In other words, we have a strain rate, a function of strain rate that gives us a stress rate. And then we integrate that stress rate equation to give us an updated stress that then we plug into the constitutive model and solve it, okay? So it's useful to understand what strain rates are for finite deformations, okay? So we'll definitely get through strain rate today, and then we'll start a discussion of stress, and then hopefully, I don't know if we'll be able to finish that today, but hopefully we'll get partway through it and finish up. Stress, not necessarily a stress in the sense of a constitutive model, but stress is sort of a geometric interpretation of what stress is. We'll work on now, and then we'll revisit stress when we talk about constitutive modeling in a few weeks. Okay, so we're going to talk about strain rate. And of course, just as we have multiple valid measures of strain, there's going to be multiple valid measures of strain rate, okay? And so just briefly before we get going, if we look at what the time rate of change of dx is, right? So d little x, remember little x is a function of big X in time, right? So it makes sense to talk about the time rate of change of it, okay? Well, that's sort of like, if we move the d inside, then that would be like dx dt, right? Which is, usually we would call this thing what? Right? This is x is a position vector in the current configuration. So we take the time derivative of that. What would we call that? The velocity, right? So normally we'd call this the velocity vector. Right? So we can kind of write this like dv. Okay? But v, remember, v is a function of, and when we're talking about velocity, we're really always talking about the current spatial coordinates, right? Because it doesn't make sense. If it was big X, it's not a function of time. It's in the reference position, right? So anytime you see velocity, we're talking about the velocity in the current coordinates, because that's the only time anything's moving, right? So remember, v is a function of, little x1, little x2, little x3 in time, okay? And we could go through this whole process just like when we did for the deformation gradient of, tracking the velocity of 2 points or their trajectories and doing a Taylor expansion and all that. But we'll just sort of save that and show you that, if we investigate just use the chain rule, if we investigate what a little change in velocity is via the chain rule, I'm going to do it in additional notation. So vi is xi, I'm sorry. vi partial xj dxj. xj, right? And so we have the name for this guy. This is called the velocity gradient. We use the symbol L. Right? So again, all these symbols that I use, like F and L and D little x and D big X, these are really the standard conventions that you'll see if you, certainly they all come from the book Malvern on continuum mechanics. So he sort of introduced the notation or standardized it at least. And then a lot of the papers that have been written on continuum mechanics will follow this convention, which is really nice. Not all of them, but it's really nice that people follow this convention, because then you can just pick up the paper and you don't have to go and try to figure out what all the symbols are. You just sort of look at them and you can read the paper rather quickly. So, you know, if you ever go on to write papers of this kind of theoretical continuum mechanics, please try to follow this notation. You'll do it, you know, your paper will get cited more because people understand what's in it rather more quickly, right? So that's L is something called the velocity gradient. Okay. So let's see if we can figure out a way to come up with what L is in terms of something we know or it's well defined, and that's the deformation gradient. I mean, the deformation gradient in finite deformation continuum mechanics is it's the fundamental notion of deformation. So it's something we'll always have or always be available in a computational code. So if we can define other quantities based on it, that's what we want to try to do. Okay. So remember. Let's see. Remember, F is D little x. I'm going to say Fij, right? D little x, or let's see. It's partial little x I, partial big X j. Right. So then let's take the time derivative of both sides of this equation. Right. And so if we do that, then on the left, we're just going to call this F dot, right? And on the right, we have, if we just rearrange, we have dvi partial xj, okay? Just using our definition that ddt of x is v, right? Okay. So then let's multiply both sides of this equation by partial big X j partial little x k. Right. Well, what is this? It's like F inverse, right? Flip it over and it's the deformation gradient, right? So it's like F inverse. So we're going to multiply both sides. So over here, I'm just going to say F inverse, okay? And if I do that, then the big X's cancel, and I have dvi dxk, right? So that is L, right? That's how we just defined L. Look right here. Right? This is the same as that. So that's equal to L. Yeah. Yeah, it is. The deformation gradient is, right, it's... Is it
delta ij plus ui?
Well, we derived it in terms of displacements, right? So it's like this, right?
Okay,
But remember that we also had that little x is equal to u plus big X, right? And so then if we take the derivative of both of these, then this is grad u transpose plus I, right? So since the right-hand sides are the same, then these two guys must be the same, right? So that's right. Right. So then now we have an equation for L. So just to summarize it all, we have the far left is equal to the far right, and just to put it in a box. I got a little bit sloppy there, right? Whenever I'm just going to correct myself. Whenever you multiply matrices, it's not like multiplying a scalar. When you multiply an equation by a matrix, you have to multiply on the same side, right? So here on the right side, I multiplied, and it's partly due to the fact I was using additional notation on one side and matrix notation on the other. But so here I multiplied by F inverse on the right. So I have to multiply by F inverse on the right here. I can't just arbitrarily choose how I do it, right? So anyway, then just to summarize and put it in a box, we have that. We have the velocity gradient is equal to F dot F inverse, okay? Which is kind of interesting because I didn't really talk about this, but F is did I use the word two-point tensor? We call it a two-point tensor because it takes things from one point to another, right? I mean, it takes little, remember what the deformation gradient does, right? It takes vectors in the reference configuration into vectors in the deformed configuration, right? It's a linear operator. It just operates on vectors, right? So it takes vectors from the reference configuration to the deformed configuration. So from one point to the other, okay? But the velocity gradient is a purely Eulerian quantity. Everything is in terms of the current configuration, right? Little x is partial little x, partial v, partial little x. So everything is in terms of the current coordinates or the current configuration. So sort of by multiplying this two-point tensor, or take the time derivative of the two-point tensor and multiply it by its inverse, these things that live in between can give you something that's purely Eulerian.